All right, we are in Windows world and we're beginning our journey of understanding how Windows 8 has evolved since Windows 7. We're with Pedro Teixeira. Please tell us a little bit about yourself.
I started in Microsoft more than 12 years ago.
Cool.
I started in Portugal, working subsidiary.
Okay, so you were in the field.
I was in the field. I was working with customers all the time. First as a product support,
Okay,
and then into an area which is product support for developers,
okay,
which they call consulting, even though it wasn't part of the Microsoft consulting team.
okay.
You would just go to ISVs and help them develop their own products and solve their problems.
Sure.
And then from that, I kind of got trampolined into being an evangelist. I started to have more accounts, and then at some point, you're an evangelist now. You're helping developers by broadening instead of being short. And it was my kind of sales department experience, and eventually I decided I'll just go to Redmond and code on the kernel.
Nice, man. So we should talk about that because that's kind of a radical change, right? I mean, you're talking about going from that lofty sort of evangelical perch, where of course you were pimping .NET most of the time, I would imagine.
And BizTalk and COM. Back then it was COM.
Back then, okay.
Back then, yeah.
So COM, well, it's funny that you mentioned
Plus.
that. COM has been reimagined, man.
Yes,
And
totally
we'll talk
reimagined.
about that a little bit later today when we get to that part of what you work on. So you came in, you're working on Windows, you're in kernel world, you're in threading world. I kind of want to learn from you today, and everybody out in the audience wants to learn about how the thread pool in Windows has been reimagined. And I'm not going to say that word again. How has it changed? How has it evolved? And kind of teach us a little bit about thread pool, how it works, where it's used in the layers of the system, etc.
Okay. A thread pool, the basic fundamental parts of a thread pool are pretty simple. You can probably implement your own thread pool in one day. Which, I mean, the thread pool consists, a basic minimal thread pool consists on a queue of work, where you put work in it, and work can be defined in multiple ways. Most of the times, the most simple work would be a function pointer and some parameter, which is usually a pvoid. And then whoever is using the thread pool decides what it is. But if you look at it, this is pretty much what your parameters are for creating a thread to begin with. Just a function pointer and a parameter. So this is a work item. First part of a thread pool. Second part of the thread pool is like a queue where you put these work items to. And on the other hand, you have multiple threads picking up work from that queue and executing it.
Yep.
And when they're done with the work item, they pick another one, and so on and so forth. So this is a basic thread pool. Anyone can implement this in one day. Devil's in the details.
Sure.
Because if you build your thread pool with one workload in mind, you'll probably build the best thread pool for that workload. For example, if you know that your work items never block, they never contend on any lock, they never perform an I/O that could block, they never do anything like that, then...
Do they do real work?
Yes.
Okay.
Well, in some cases, like embarrassingly parallel things, like a subcategory of them, they might actually be like that, like calculus,
Sure.
where you're just crunching numbers on those work items. It solves a lot of problems because how many threads do you need to be optimal, to run at perfect speed? Number of cores, right? You have if you have one thread per core, you keep all the cores busy all the time.
Yes.
Now, of course, if you know that you block like 3 times per work item, you estimate how much time you're blocked versus running. You take that percentage and use that percentage to multiply by the number of cores, and you have the number of threads. You probably have the best thread pool for that workload. And that's why Windows had dozens of thread pools lying around in the system, homegrown. Few thread pools in Internet Information Server, thread pools in the I/O Manager, thread pools in BitLocker, all thread pools lying around. This is a lot of code to maintain. It's a lot of surface, it's a lot of footprint. A while ago, and for the kernel mode thread pool, that would be before the 90s. For the user mode thread pool, more recently, there has been the attempt to create a thread pool that could fit it all, so that people trying to tackle their problems, networking, HTTP, bit security, could come out of that thing of implementing their own thread pool and use this one common system that could not only not regress what they have, but actually be better. Of course, that means that this thread pool has to be very versatile. It has to really, really adjust. So simple answers like, oh, I have 3 threads or 4 threads, or 3 times the number of cores doesn't work. Because if you have a workload that blocks a lot, and we do find a lot of work items that are put into the thread pool that block a lot. We even have work items that open windows and wait for user input.
Sure. Well, that would be a modal dialog, for example.
Exactly. Then having a rigid number of threads servicing a thread pool is not a good thing, because if the thread is blocked, and if you have, for example, equal number of cores, then equal number of threads, then you lost a core. You lost performance. Your entire pool is running with 1 core less, effectively. So one of the biggest problems about thread pools is governing the number of threads and self-adjusting to what is going to happen, to what is happening. Even before Windows 8, in Windows 7, we already have, and this is actually a part of the system that has been there for a while, which I/O completion ports. I/O completion ports allow you to only have a certain number of threads running.
Okay.
And basically, the number of running threads self-adjusts to the number of cores. Because the other problem is, if you have too many threads, I mean, you can always say, okay, if I have too little threads, then I'm losing cores. I'll just create a bunch of them.
Yeah.
Create a bunch of them, way more than the number of cores. And even if a big percentage blocks, I still have plenty of them. Well, that has 2 problems. Well, footprint cost. Threads, well, they're not big, but they're not cheap. They're not free. The second one is that if they're all runnable, if you have a lot of threads that are competing for the CPU, you'll have context switch, undesirable context switch between threads. Your performance goes down. So this kind of defines a big principle on how you want to design a thread pool. Do you want your thread pool to start running work items that you put in as soon as possible? Like as soon as possible, even if it injures performance, you're pretty much in the field where you could just create a thread. It runs as soon as the scheduler decides to run it, which will be in the immediate future. And if you're causing an overscheduling, you're harming performance. Most thread pools, and including the Windows ones, operate on the batching model, which means that work goes into the queue and gets picked up when it's optimal to do so. So when a core becomes available. One work item, so one thread will not, if the number of cores is taken, so if you have 4 worker threads on a 4-core system and they're all consuming CPU, even if there is a gazillion work items in the queue, they will not be picked up until one of these work items either blocks or finishes.
Okay.
Now, blocks is the interesting part. Finishing is obvious. Block is the interesting part, because if it blocks, then you allow another thread to pick up work and start running. That's where the I/O completion port comes in. This is a standard feature of the I/O completion port. You create one, you assign a number to it, usually the number of cores, even though you could adjust it. And the I/O completion port allows, which is basically a queue with a concurrency control assigned to it, it allows work to be pulled out of the queue, but at the same time it measures the number of threads that pulled work if they're taking CPU or not. So in this case, you have 3 threads. They're actually running. They're consuming CPU.
Okay.
let's assume you have a fourth thread here, but you only have 3 cores. It's a very weird machine.
Yeah.
You have actually work in the queue, but until one of these either finishes or blocks, well, in this case blocks, this thread is not allowed to pick up work. So all your cores are taken. There's work here. This thread is waiting on work to come. On work to be picked out, so it's blocked. But it actually isn't able to pick it up because all these are running. Now let's say one of these blocks. It's not taking the CPU anymore. I/O completion port measures that. The number of active threads is now 2. Number of cores is 3. So this thread is unblocked and picks up work. I/O completion port. Cool. That is fine. That's basically, if you're going through for this model, you're in batched world, it means that you are favoring performance over latency. Because you never know when your work item is going to be picked up. It depends on the work items ahead of you. If they spin in the CPU for a long time, they don't block, and if they take a long time, your work item could potentially be in the queue for a long time.
Okay.
Nonetheless, it's guaranteed that the work items will run at their top performance because you're not overscheduled. You don't have 10 threads running over 3 cores and then having to context switch between them before they were done with the CPU. And that would be a waste.
Absolutely.
What I described here is basically Windows 7 thread pool. User mode 1. I'll go to the kernel mode, it has a different set of problems, but this is the user mode 1.
Okay.
The biggest challenge with this approach, we're getting to the second level. Now you could address this all in user mode. You could write all this in user mode. But we came to the conclusion that it was not enough to have just user mode thread implemented 100% in user mode. Why? Thread creation. I drew this 4th thread here, even though we have 3 cores, right?
Yep.
But I kind of assumed there was one here already, kind of waiting for one of these to block to pick up work. Why is it there, and how many should there be? Second problem, thread creation policy. That's the main thing that we tackled in Windows 8.
Nice.
How did it used to be, and how it is in pretty much all the implementations out there that I've seen, even in other operating systems. If you have work in the queue, and you're not concurrency bound, so you have available cores, you create another thread, and so on and so forth.
Okay.
And you keep on creating them. And then they eventually die if they time out, if they're not assigned work for some time. If some time is passed and the thing shrinks down, potentially to 0, if you're not putting work anymore. Biggest challenge for this, and this actually was pointed out by the Internet Information Server folks.
Okay.
Because they replaced their thread pool during Windows 7 timeframe. They tried replacing their thread pool, which had their own logic, with the system-wide one, and something really interesting happened. Their work items block in them, and they block reading a file. And assume that this is a website, and you have index.html, your homepage.
Yes.
And you have a big box with a lot of CPUs, a lot of memory, very powerful. With this policy alone, let's say that you have thousands of clients accessing the homepage, and the homepage is not in memory. It's in disk. So a work item is queued, wants to read the homepage. Another client comes, wants to read the homepage. Another client wants to read the homepage. They all block on the same resource, index.html first page.
Yeah.
If, with the current hardware, well, current as in Windows 7, already what happened is, before the disk had time to go and move the head, and pick up index.html and transfer it to memory, the policy had already created over 1,000 threads. And now note that all these threads are contending on the same resource, which is the same page.
Aye.
I could give you other examples like all the work items. Let's say that all your work, that's probably a bad example, but there's plenty of examples of that, like that. All your work items take the same critical section at a certain part of the code. That one blocks, another one picks up. That one blocks, another picks up. So we really need to work out these things that we call thread explosions, so that we don't just create threads at thousands.
Sure.
And then all of a sudden, it's not helping. Creating more threads and having them then block in the same resource, it doesn't help performance. It doesn't help anything. It just harms your footprint.
Sure.
So what we did was we added some rules to the thread creation policy. Now note that we can't just say we don't create more threads at any random given point. Let me give you an example. Let's say you have a queue of work, right? And let's say you have a bunch of work items running. They all block in the same resource. And for some programming error, the work item that releases that resource is in the queue. This is what we called popular internal dependency. All these work items depend on the queue. Now let's say that at a certain point you reach your safeguard number of threads, maximum number of threads. You can't create more threads. All of these are blocked. Or you decided not to create more threads. No, it's 4, it's enough. I only have 1 core. Done with it. Everyone's blocking. I'll just not create more threads.
Okay.
It means that this work item never runs. It never releases that resource everyone's waiting. You have a deadlock.
Yes.
Another very typical example is I start an operation and queue a work item to complete it. This guy runs, queues a work item, that queues a work item, that queues a work item, that queues a work item. It means that when this guy runs, let's say this one is the last one.
Okay.
When this guy runs, it releases this one, that releases this one, that releases this one, that releases this one. If this guy doesn't run, you have a deadlock. So what are the things that we want to detect? What we call the popular external dependency, which is there's some resource that it's not in this pool of threads, and this would be the best example for this. It would be that index.html page.
Okay.
That is, the disk is holding it. Everyone is depending on them. Dequeuing another work item that will eventually depend on the same thing, it will not help. It will just not help. The problem is, so this is what we want to tackle.
Okay.
Or the same thing, which is this guy depends on this guy, depends on this guy, depends on this guy, and then depends on this guy.
Okay.
Not creating more threads here is good, because this is a thread explosion case. The problem is that to detect if this is a thread explosion, we need to go back in time. We need to run this guy and then realize, he's going to block in the same thing. So let's go back in time and not run it. We can't do that yet.
Anti-threads.
Yeah.
Okay.
Antimatter.
Yeah. All right.
So here comes a very, very slippery slope subject, which is heuristics.
Okay.
And that's why we came to terms where to make an effective thread pool, we need to have something in a kernel that helps the user mode portion know what to do best, provide data, and actually decide how to create a thread. It's mostly to create threads.
Sweet.
What we did is that we have creating a thread has a fixed policy, which is the one I described just a little bit ago. You're not capped on CPUs. You have work in the queue. You have not reached a artificial maximum or resource maximum. There we go. Create a thread. But then there is a second part, which is the heuristics part, that does not totally veto creating a thread, but introduces delays. So as the kernel is releasing threads from the kernel to run work items, as a response to the user mode portion asking for more threads. Hey, give me one more worker thread. Give me one more worker thread. The kernel is keeping a tab on the a handful, the last recently released threads from the kernel. So let's say the last 10.
Okay.
Last 10 threads that left the kernel. And at a given time, the decision to create the 11th is coming by. And the kernel is going to look at all the threads that you released. And it's going to look at what are they doing? Are they blocked? If they're blocked, are they blocked in a single resource? And if that single resource is popular. So basically, let's say these were 4 threads, were the last 4 threads that were released from the kernel. And we're considering whether or not it's good to create another thread to run this guy. We'll look at these guys, they're all blocked in the same resource. We released last 4 threads, all 4 threads are blocked in the same resource. This is a thread explosion. And based on the certainty that this is a thread explosion, a delay will be introduced on that thread creation. If we're really certain that this is a thread explosion case, and that there is a high probability that this guy is going to contend in the same resource, because everyone else has it, the work item looks the same, it's the same function, so it's probably going to go that way, then we assigned a very high probability of it going into thread explosion and delay the thread creation by a big amount. If we're kind of mildly concerned about that, we're not so sure. There has been other work items here that did not go that route, but it's still on the 60-70%. We introduce a very small delay. When that delay expires, so let's say 30, 100 milliseconds later, depends on the band, we ask the question again, do we still need that thread? Has this thing been resolved? In a lot of cases, it has. If it was really a popular external dependency like that index.html, this guy released the lock.
Okay.
These guys started running, at least a few of them started running. We run the policy again, and thread pool kernel portion, which I call the work factory, says, you're right, this thread wasn't needed. On the other hand, if after that delay we look, no, this is holding. I think we might be heading into a deadlock situation. So let's create the thread then.
Okay.
That's what we did, basically. In a nutshell, that's what we did. We have a heuristic that introduces delays depending on the likelihood that this work item is going to run into the thundering herd of a one resource.
Okay. Now, what happens if you're, given the sheer number of things that can happen in a galaxy of an operating system? What happens if your heuristics are wrong?
Well, we've spent kind of half a year tuning them.
Okay, great.
An heuristic is like a small blanket in a cold night.
Okay.
You pull it to cover your head, your feet are cold. You're trying to rotate it so that you get most of your body covered with it. And that's what we did.
Okay.
I mean, with heuristics, there is no 100% certainty. That's why we don't decide to just not create a thread. We just introduce a delay.
Okay.
For example, the Internet Information Server thread pool that did not have the thread explosion problem, they always introduced a delay. That was their policy. They always introduced a delay creating a thread. So they had a thread explosion problem, but it was really slow. So pages would eventually come back.
I see.
When they were replaced with ours Win7 one, which does not take a delay at all, it exploded. So we decided to take that route based on heuristics, based on incertity and certainty, but with an algorithm that allows it to correct itself.
Great.
Good thing is that on all the testing that we did, our performance was never injured. It was actually improved.
Nice.
Because you have less threads. You have less footprint, you have more locality. So you have a lot of more tight execution. We had not one case where this caused a delay.
Excellent.
We had cases where this caused a huge benefit. Let me give you an example. If you use the thread pool on .NET, .NET has one thing which is called the garbage collector.
Yes.
At some point, our garbage collector decides that it needs to freeze a bunch of threads. I want to freeze them all because I need to look at their stack, look at what objects are still referenced, and then collect those that are not. Fine. you have someone suspending a bunch of threads, causing a bunch of threads to block. What happens to the thread pool if they're thread pool threads? Create more threads. There you have garbage collector trying to block threads, and you have the thread pool trying to create threads. It's like a race.
Yes.
So it was very complicated to use effectively the Windows thread pool on .NET. We tested this new thread pool on .NET. We ran the worst garbage collector stress that they had. It created 3 threads over.
Nice.
Instead of thousands and thousands in an unbounded circuit. And then eventually the test stops, and then it's 3 threads over.
Awesome.
So it was very important, especially with the new applications being developed on WinRT, with C#. That was really important to make sure that this thing was correct. So yeah, we spent a lot of time. Yes, of course, you can go about and open Visual Studio and code a bad example. Yeah. Now that you know this,
yeah,
you can code a bad example. You can actually measure. You can create a bunch of threads, all of them waiting in the same event, and you'll see thread creation performance, or the rate at threads are creating going.
Awesome.
You can measure this, and that's what we want.
Good.
Because we don't want you to code that way.
Yes.
So how did this come to be in terms of architecture of the user mode thread pool? Where do you want kernel to be?
Kernel.
We're the kernel guys, so we always put it on the top.
Put it on top. I mean, we usually put it on the bottom, but you know, I think you should put it on top. Put it on top.
Really?
Because I'm tired of seeing user mode on top.
All right.
We always do that.
Kernel.
Yes.
So we have one thing, which is the worker factory.
Okay.
This guy is responsible for creating and reusing threads. This is where that heuristics is, and this is where the policy is. And then you have a user mode portion. This guy lives in NTOS, actually. And this guy lives in NTDLL. The core part of it.
Got it.
And this one is the scheduler. This guy assigns work to threads. This is where the work queues live. Priorities and things that I didn't talk about that can make a thread pool even more complicated. Priorities, different priorities. So this is where threads come and work is assigned to.
Okay.
And then go about, and then comes back and validates if the thread is in the same state, assign it to a new one. Most of the time, the scheduler is able to assign work to threads back to back without even talking to the kernel. That's why it's so performant. There's no ring transition, nothing. It's just dequeuing work items and going about running it. When the scheduler comes into that part of, oh, I do need a thread to run this work item, it doesn't know if it's going to get a fresh one or reused one, doesn't know. Sorry, first thing, when the scheduler never blocks. So if it doesn't have a use for a thread, gives it back to the worker factory. Go. I don't have work for it. Just go. Goes back to the worker factory. And it has also a different channel, which is, I want a thread to run this work item. My demand has increased.
Okay.
Note that these channels don't actually operate if you're in a steady workload. Your number of threads is always optimal. So you don't do ring transitions. You only do ring transition if your load is going down, you're returning threads back to the worker factory. Or your load is going up and you're asking for threads from the worker factory. So you return threads back, and this is where the threads get parked for a certain amount of time.
Okay.
Until, oh no, I really don't need them. I'm just going to toss them. Or, oh, I really need to create them based on the policies that we just described. Create one and give it back. Most of the time what happens is that it reuses a thread. Came back, work came back. It's only, so the heuristics and logic only runs when all the threads are in use, all the threads I worker factory have, are in user mode. I'm being asked for a new thread. Should I create it or not? So this is basically the architecture of the base architecture of the thread pool. Scheduler, worker factory. Now, there's more to it. We wanted to produce a thread pool where people could code to the continuation model. Actually, WinRT requires that. You don't block. You just code to a point where you could block, and then code the part that runs after your operation in a different, a continuation. And they, if you're right,
async, whatever.
Exactly.
Yeah, very highly asynchronous. We're gonna talk to you about that for sure, because it is a purely asynchronous model.
We want that to be as simple as possible for people implementing iasync for network, iasync for file, iasync for the thread pool, WinRT thread pool itself, to do this very easily. Queuing a work item manually, hey, here's the work, queue it, run it as soon as possible, is the simplest of them all. But in order to do continuation effectively, especially if you're doing IOs, network, and all that, you need work items that are queued automatically based on things that happen on the system and not on the application. For example, in the case of the IO, I want a work item to be queued when the IO completes, not when I queue the work item. So thread pool has TP work, which is an object that represents work that you queue and you want to run it, the application-driven work item. And then it has TPIO. This is from Win7. This is actually from Vista.
Okay.
TPIO, which is work that gets queued automatically when a IO completes. TP wait. And these are the ones worth mentioning, which is work that is queued automatically when an event or semaphore gets signaled. So now you can really do continuation, because you can queue work condition on an event being signaled or on an IO completing. You can just make those pieces of code. And if you're using await, they actually look like a continual function, but they actually are different functions that run potentially in different threads.
True.
Now,
but the key there is that it's fine, and the whole goal is so that they don't run in the UI thread.
Exactly.
Which is the most important thread to leave the heck alone.
Exactly.
When you're doing a lot of computation.
But note that even if you're even if you're not in the Metro world.
Yes.
Sorry, I used the Metro.
That's fine. You know what? Sometimes mistakes happen. Windows Store app world.
Windows Store app world. Okay, even if you're not in the world.
We'll hear Metro a lot, over the coming year. I think the key is,
it's a code name, right?
Yeah, just you said it in quotes. We're good. Okay.
So even outside of it, continuation model is the one that making your code into small, grain fine tasks is the one that allows you to scale the most. Because if you make one big thread, you can't parallelize that with others, and you'll be holding a thread hostage while you're blocked. If you want to be the best scalability possible with the lowest footprint, you are indeed, even if you're using C code, you are indeed better off using the continuation model. Of course, when RT brings that upon you, which is good because Visual Studio guys did awesome language extensions that make that easy with the lambdas and with the await keyword, which makes possible to use continuation model while typing as you learn how to type code a decade ago.
And the C++ guys get PPL.
PPL, there you go.
So they get to use tasks and all that stuff.
But basically, you're using the continuation model. So back to these two guys. Now, the last big improvement that I'm going to talk about in terms of the user mode thread pool is I mentioned that the work queues are in user mode, right? Work that TP work gets queued directly into these guys. Now, TPIOs and TP waits can't. They are kernel accidents that happen. They happen in this world, right?
Okay.
The IO is going to finish, and the ERP is going to be delivered somewhere. Now, it's going to actually be delivered to the worker factory, which means that to some extent, the worker factory does transport work. But it couldn't care less about what work it is, and it certainly doesn't decide to execute them. But if there is a thread waiting here, so one of those threads parked, the worker factory releases the thread to user mode, even without the user mode asking for it. And the sole purpose of it is to transport work. Now, the way this was rigged in Win 7, it only happened when these queues were empty, which means that if you had a lot of TP waits being fired and a lot of TP works being fired, this was unfair towards the wait. You could run thousands of TP works before you had the chance to run a TP wait, because it took the scheduler it took the scheduler needed to get to a point where I should check for kernel work, I guess. And then the thread would come and bring one work. Now, what we did is that we actually incorporated wait objects into the I/O completion port and the I/O completion port into the worker factory. So we made, there you go, more need for half code in kernel, definitely.
Yeah.
In a way that the worker factory can, on its own volition, release the thread to user mode to transport work.
Excellent.
And it doesn't transport one at a time. It transports a heap of them. So even if there was, and it will have that frequently, very frequently, even if you have a lot of IOs completing at the same time in a very load machine, and your CPUs are very high, so your threads don't get to run immediately. What happens is very frequently, this thread actually transports, in average, on a very load system, about 16 work items. When it gets to user mode, it requeues all of them. It requeues them to the user mode queue. So now they're in equal terms with TP work, right?
Yep.
They're in the same queues. And the thread is now available to run one of them if the scheduler decides it's a good thing to do. So now we have all of these guys are actually behaving the same, with the same relative priority or importance. And that was a very important thing now that we're depending so heavily on these for continuation model in the modern world.
Excellent. Now, what about, you mentioned, one of the things about the properties of threads you didn't get into, as you mentioned earlier, was priority. And on Windows, you have a bunch of applications that, of course, want to have the most priority. Outlook, my God, we must check mail, we must do, whatever.
The responsiveness.
Yeah, responsiveness and trying to get background processing correct. It's not easy. But talk to me about changes there. How does this impact that world? Does it?
Well,
I mean, it probably doesn't, but I mean,
what we had already in terms of priorities, we basically have zero. To some extent, we have Xerox copies of this per priority.
Okay.
Not all for example, the worker factory is mostly single priority. It knows the priority that it needs to create to and creates to that. But the worker queues are just Xerox copies. And you have a queue for priority A, Y, and B. We actually, on the user mode thread pool, we only have 3 priorities.
Okay.
Which is normal, below normal, and above normal.
Okay.
So
there's no extra above normal and super incredibly above normal.
With the current need for responsiveness and to avoid priority aliasing and priority inversions, we may have to go in the future to a full spectrum of 31 priorities.
Okay.
Definitely right now, what we observed is that, especially for the user mode case, with the kernel mode, we have more priorities.
Sure.
For the user mode case, these 3 priorities managed it well.
That should be fine.
Let me give you an example of how this made an importance.
Okay.
I probably heard of application request routing. It's one of the APIs you can make really scalable 3-tier web applications.
Okay.
Application request routing with this algorithm on Windows 7 per transaction. A transaction is a bunch of operations that require works and IOs. It was about 2.3 context switches per transaction. Windows 8.
Nice.
0.7.
Very nice.
This gave us an increase of performance of
very nice. Excellent work.
Yeah, this was. I mean, it was not only for the explosion that was important in that case, but also the TPU work and the TPIO and this thread that we actually kind of inject and brings all the work down and keeps all the work in user mode. And our average work transported by this thread was 16 work items at a time during heavy load.
Nice.
On average, which means 16 less ring transitions to carry work.
Great.
And this is pretty much the user mode thread pool. It covers all the user mode thread pool.
Yes, thank you. I think it's, if anyone didn't understand what a thread pool is, now they do. And they also understand how Windows provides at the system level a very modern one. And clearly you guys have solved a lot of relatively hard problems, I mean, for sure, in the general purpose operating system space. You don't know what people are going to do.
Yeah, that's the problem.
You just don't know.
The bold goal of providing a thread pool that could fit all shoes.
Yes.
That could fit all feet. It's one that would require, okay, we have to take all the workloads. Workloads that are written the way we think workloads should be written, and workloads that are written the way we don't think workloads should be written, but still we need to run them as best as possible.
Absolutely. Now in the WinRT case, so of course WinRT is the new programming ABI libraries for user mode programming on Windows 8 with this new application model and Windows Store apps and things like that. Very modern, very fluid, very fast, very asynchronous, as you mentioned.
Very asynchronous.
So in that case, does WinRT has its own thread pool that was implemented by the WinRT people? Or do they use what you're showing us there on the bottom half of the user mode thread pool?
All this.
All of this?
It's all this.
Okay.
So if you're, for example, using the WinRT socket API,
okay.
Under the covers, that object that represents this network connection is using a TPIO underneath. And actually, there is another layer in the middle of it because sockets support MMCSS, the multimedia scheduler. So there's a layer above it that allows the worker threads to be on a MMCSS scheduler. And then on top of that, the WinRT sockets API shows up. But they're calling this API.
Great.
We do export also, we created ourselves, a WinRT thread pool API. One that you can use to queue work, like to represent mostly this.
Okay.
And you create a lambda or you use a wait or whatever.
Or then in
or
JavaScript.
Then, and you throw that object into the WinRT thread pool. Windows system threading.
Whatever it's called. But that's just a thin wrapper on the
It's
user
a thin
mode
wrapper.
scheduler, which is not called the user mode scheduler, by the way. It's called what?
This is the thread pool scheduler.
Thread pool scheduler,
Yep.
thank you.
So in that case, what we do is that layer around it not only makes it, addresses all the reference counting. So when you're passing in that object, which is your delegate, it reference counting the delegate, and it's going to keep a reference alive. So if you want to fire and forget, thread pool will release it for you by dropping that reference. It makes sure that the threads are MTA initialized before your work item starts running. And it also actually keeps those threads while they're living before the scheduler decides, or actually the worker factory decides, I don't have any use for these anymore. It keeps them WinRT initialized for MTA. So we are not paying a tax of creating threads, we're not paying a tax of initializing WinRT every time we run a work item.
Excellent.
Also, one thing that is pretty hard to get right when you're using thread pool is that the parameter, the parameters that you pass to a work item. So if you want to pass state to the work item, you have that p void that I mentioned.
Okay.
Let's say you want to cancel that. You queue a work item to the thread pool. It could be, for example, a TP wait, and then you're exiting. For example, I don't want that TP wait anymore, so I want to cancel it. If you want to cancel it, and then what do you do with that memory you allocated and passed on a p void? Do I release it, or was I in time to cancel it? Maybe the work item ran. Maybe it's running now. Maybe it is going to release that data. Who is going to release that data? Me or it? The fact that thread pool is actually handling those references. So you just call cancel, and that's that. If the work item is running, the reference is held. If the work item is executed already, the reference was already released. If it hasn't started executing and it was canceled correctly, successfully, then the reference is dropped at that point, and the state is released. So you don't have to worry about that anymore, about the releasing of the state that you pass. It's also a good thing that delegates are now not only a function pointer, but they're an object that has a reference counting. So basically, yes, what we did for the thread pool, WinRT thread pool API was to put basically an ABI, WinRT ABI, around the C-styled Win32 thread pool and make sure it covered the cases there.
Absolutely, and I would imagine that there's some, you also, by providing an ABI surface, you essentially define what you can call.
Exactly.
Right? What's safe, what's not safe, what fits into the WinRT model.
In most cases, yes. So we started slow. If you look at the API list for the Win32, it's big. It has a lot of knobs that you can tune in. For the WinRT, we want to make sure that it was very simple to use and covered, if not all of it, grand majority of cases. We actually support queuing a work item, something that we don't have on the Win32 one, other than creating your own thread. We actually support queuing a work item with non-batched, so with time sliced. If you queue a work item using time sliced versus batched, which is the default, of course, that work item will run over scheduled. It was a very important thing, but again, in WinRT don't create threads. So it was a very important thing, especially for gaming, where in some cases it's quite crucial to have one continuous work item that runs at low priority, and it's always wants to run if nothing more important is there to run, like looking, processing other parts of the map of the game.
Understood.
So they needed that time sliced option. They needed to have latency over throughput. So we provide that option to use in those cases.
Great, and I mean, it makes sense. I mean, games are typically played full screen.
Yes.
And in fact, in the Windows Store app model, or WinRT, you're running in full screen anyway. Your app is what is running. So that actually makes sense, depending on, even if you want to build a Maps app that isn't a game, as you just mentioned. You said the term map, but it's all graphics and rendering graphics in the background.
Getting other,
Exactly. Very, very cool.
That's a very good example.
So it's really nice to always come and talk to kernel people. Now, you live in the world of C, yes?
Yes.
Are you writing any C++?
Well, for this we had.
Yes, okay, well that's good to know.
Yeah, the WinRT thread pool is all written in C++.
Okay.
ABI.
The ABI is C++.
Yeah, it's all written in ABI, and but all this is C.
C.
In the kernel world, we very frequently have to use assembly. We try to keep it as tight as possible because it's harder to maintain, and you have to write it for more platforms.
Sure.
You can't write the same C.
So I mean, yeah. So you're actually, I mean, you can't write more C than assembly. I mean, you write more C than assembly in the kernel.
Yes, yes.
You must.
Our ratio is we only write the assembly in assembly whatever we can't live without. For example, an interrupt handler prologue.
Okay.
I mean, the CPU is throwing at us registers and machine frames. We need to process them in assembly. But as soon as we collect that information, we jump to C, because chances are we can have that code be the same for all platforms.
Yes, it's one of the good things about C.
Yeah.
But assembly, of course, is hardware specific. I mean,
yes, you have to write it 3 times.
I mean, you have to write it.
Not that this saves you from writing the same C code 3 times. We have parts in the kernel that are written in C, but they are still platform specific.
Okay.
For example, the code to attach an interrupt. I mean, CPUs are different, even
Sure.
though you can write them in C, which makes it easier to maintain. There's value in writing it in C. It still has to be written 3 times. Or the boot definitely has to be written 3 times. But yeah, the assembly being what we try to keep away as much as possible. And then second level, 3 Cs.
Three
Three
Cs.
assemblies, 3 Cs, and then what we try to keep ourselves the most part of the time is one common code that can fit all, that is platform independent. And thread pool is all platform independent.
Nice. Excellent.
Yeah.
Well, hey, awesome, and very, very nice work. And it's great to see this level of innovation at the thread pool layer, both in the kernel and in user mode.
Yeah,
So-
I hope people really. We got a lot of feedback from our internal products, or our internal partners, like the Windows server, like file sharing. They got a 12% boost. From the Internet Information Server, BitLockers, and all that. We got feedback from them, but we really want people out there just don't implement their thread pool, use ours, and hopefully if there is something that doesn't work, we can fix it.
Absolutely. And this goes for desktop apps and WinRT apps.
Absolutely, yes.
Rock and
Classical.
roll, man. There's also the kernel mode thread pool.
Yep.
Talk to us about that.
The kernel mode thread pool, it started off as an extension of something that already existed from the 90s, which was the executive worker factories. If you have that Windows internal books, fantastic. You go to the chapter called EX Worker Queues, that's what it is. It was designed initially to address a very simple problem in machines with very little number of CPUs. Drivers need to run things at passive level. And drivers can run an interrupt, hopefully for not too long. And then they can queue a DPC, but at DPC you can't block, you can't page. So drivers need some way to go down to passive level and run something that can incur in page faults, block, et cetera, et cetera. Initially, again, we had one queue, which was an I/O completion port, and a fixed number of threads, a very small one. And there were 3 priority levels of them. Actually, in one priority level, there was only one thread, called hypercritical, only had one thread.
Okay.
And these are like 7 and 5, I believe, for the critical and the delayed. Now, the short number of threads was only for, remember, this is not to address parallelism. There's no point. The machines don't have a lot of CPUs. In the kernel, the work items are always short. We don't have all those problems of panacea of different workload types. They're different. A BitLocker work item will not be the same as the video capture device or the graphics card. They're going to be different, but they're always very short, very contained, very already continuation model kind of thing. So our the biggest problem here is that it wouldn't address parallelism at all. It was built to solve the problem of going down to passive. You could solve that problem with one thread per priority level. Of course, one thread has a problem, which is that thread is now very valuable. If some work item takes a little bit longer than expected, other things will stall, even if you only have one core. You probably prefer to have a little bit of context switching there than to crash the system with a DPC timeout or something like that. Or a power ERP timeout.
Yes.
So we decided, no, we're going to make it into a thread pool. A really thread pool, you can, people like BitLocker that are decrypting the disk, they can like throw a thing at it and it will paralyze and it will address performance the same way we want the user mode thread pool to do. Small set of problems, again, small set of problems in terms of how the workloads shape up. But, so, first thing we had to do was we had to make this NUMA aware. This was one queue for the entire system. So for big iron, which there are different NUMA nodes, do I need to explain what NUMA node is?
Well, we covered NUMA a little bit. I mean, that you can do it briefly. It's basically guaranteeing that you have locality in memory.
Exactly. So in NUMA systems, which today pretty much any machine that has multiple sockets, multiple actual sockets, is a NUMA machine. There's a concept of nearby memory and far memory. Memory that is attached to the memory controller of that CPU is very fast. Memory that's attached to another CPU is not so fast.
Sure.
So you're better off communicating with the memory on your node than across.
Absolutely. Great.
This is very important, especially on drivers and stuff like that. We really need that locality. It's really slow. So we created, and this in the kernel mode thread pool, this is really totally Xerox copies of them. There's nothing shared. We don't have work stealing out of policy because of one thing, which we have in user mode. I didn't cover that, but there's the possibility of stealing work from a different node. But there's a reason for that, is that we create these threads and their stack is also in the same NUMA node. So the work item is for that NUMA node, the stack is on that NUMA node. There's no reason to go cross nodes.
Great.
We even have a new API that allows you to queue a work item for another node, for example, if you know that the data that work item is going to process lives there. An example of this is freeing pages, lazy freeing pages. And another thing that we did is we actually added a dynamic thread pool thread creation policy. We used to have just a handful of threads, and now these can actually grow to a few thousands. So you can parallelize in a machine that has potentially 600 and something CPUs, which we can with Windows 8.
Great.
Again, it won't just create a bunch of them. It will only create if they start to block a lot. But then again, if they start to block a lot, you have other problems.
So it's the same heuristic, only different.
We don't have the delay. We didn't thought it was, based on our measurements, we didn't thought that the workloads ever created those dreadful popular dependencies and internal dependencies, zigzags and long dependency chains. We didn't observe them, so we didn't create that part, the heuristic part of it. But the policy is exactly the same. There was work in the queue, whether the CPUs are capped or not. So the same base policy, yay or nay, to create a thread.
Sure.
Another thing this addressed parallelism. We were able to address parallelism. The last thing we did really need to do, and this was a major problem in the previous releases, is that our storage stack sometimes needs to process things also at passive level. A thread pool that may need to create a thread to process a work item has a danger point, which is if you need to create a thread, you need to allocate resources. That's a failure point. The user mode thread pool handles that by trying later when the resources go down. But the kernel mode thread pool may not afford that. Because if the work items that release memory are in the queue, you have a resource deadlock, right? Because the work item, you need to create a thread to run work items. You are out of memory. You can't create more threads. The only thing that could release resources is in the queue, waiting for a thread to be created. This actually caused things like the file system to have threads dedicated, always created just for this case. Bunch of threads so they could be parallel. The server service, the same thing. Filter manager, VHD, native VHD, all those guys needed because they are in the storage stack. So they are handling page outs, release of physical memory pages, right? So we needed to have some sort of a guarantee for progress for these work items that are so critical. So what did we do is we added an API. So again, we have a queue which has, let's say, 4 work items in it, and we have 5 threads.
Okay.
And they are waiting on the queue. Maybe they didn't pick up work yet because there are 4 cores and there are 4 threads, extra threads that are processing. So these are just waiting for that concurrency count to drop so they can pick up work. Using this new API, drivers can try submit a work item to the pool and have a positive or negative response based on whether or not it's guaranteed to have a thread. In this case, you have 4 work items in the queue. Okay. You have 5 waiting threads. If you queue a work item, to the queue, at this point, you're guaranteed to have a thread, right? Even if all of these block and never return, even if all of these pick up all the 4 work items and never return, they all block in lack of resources or something else, this 5th thread will handle that request you're about to put. Now let's assume we have the opposite. We have 4 work items in the queue. We only have 3 left. You don't have that guarantee. Because in order to run, if all of these threads block, for that 5th work item to run, I need to create 2 extra threads. And I may not be able to. So that API will respond, no, you cannot create, you cannot queue a work item. I will not queue it for you because you use the API that requires forward progress. What can drivers do in response to that?
Yes.
First of all, one of the alternatives, NTFS uses that, is that, okay, I'll just run the work item in line. Instead of parallelizing it, I know that this only happens when you're really in a tough situation, right? Your resources are down, everything's blocking, you have a lot of work piled up. You get that negative response, like, okay, fine, I'll just run it inline, not parallelize. Hopefully you will free that page, and then you can create that one last page that allowed a thread to be created, and then when I queue it again, I'll have it. Yes, because when this thing responds, no, I can't do that, it will try to create another thread still.
Okay.
So that the next response will hopefully be yes.
So it itself knows that there's some issues going on that it can't do what it's supposed to do.
That's the biggest thing, that all of this has awareness on resources. Both the user mode and kernel mode, they respond just differently. The kernel mode has awareness of resources. This is going down, this is getting really tight. Okay, I'm totally tight. I can only count with the threads I have right now. And I'm just going to fill a form to try to get a new one as soon as possible.
Cool.
So now drivers can choose multiple things, which is to run them in line, or if they need, they can have an emergency thread. One, not many, because the problem we have is that all these drivers, storage drivers, they needed parallelism all the time. But they wanted forward progress, so they needed to create a bunch of threads, static threads, to handle their resources. Now they can create just one, and have that just used for when this fails. So in the good case, the common case, you have full parallelism that shrinks and grows and whatnot. In that one case, you just need one thread to run that work item. You don't need parallelism. Your machine is actually pretty hosed right now. So you don't need parallelism to do that. Another thing is that drivers sometimes get re-entered. I'll give you an example. If you have a VHD inside of a VHD inside of a VHD, NTFS is called 3 times to handle one I/O, one page out. If your page file is inside of the VHD, that's inside of the VHD, inside of the VHD. Which means that NTFS to handle one request may need 3 emergency threads. Depend on how it knows that it's re-entered. What I'm saying is that we decided not to tackle the emergency thread or the backup plan in the thread pool because different drivers need different things. Some drivers may run in line. Some drivers may need more than one emergency thread. Some drivers may need one emergency thread. And that's why we left that to the driver writer. But we wanted to make sure that we had a indisputable response from the thread pool. If it returns true, it is going to run.
Great. Now, in Windows 8, so in Windows 7, there was a kernel thread pool. But not quite to this.
It was for the one from the 90s. So 1 queue, 3 priority levels, and some of it was like, I don't think it went above 15 threads or so.
Great.
It was only to run things at dispatch, not to get parallelism.
Understood.
That's why all drivers
had a different problem
thread
back then.
That's why the server service kernel driver had a thread pool. That's why BitLocker had a thread pool. That's why all of these guys had a thread pool that now it's ditched, and it's using this one.
Excellent. And you give people the flexibility to, I mean, people who write drivers and at that level, people who engineer at that level, sometimes do need, the flexibility to not rely on a thread pool.
Exactly.
Which that is afforded to them in the kernel. That said, when they make that leap, there's a possibility that their code can crash the entire house.
Exactly.
So they need to be very, very careful. And this is a very highly performant, scalable, reliable thread
The
pool.
reliability there being is the reliable there being the key word, right? Because now you can make an educated decision whether or not you're going to use at runtime, whether or not you're going to queue that work item to the thread pool or not. Because even a driver, even NTFS, it may queue to the pool, and it doesn't guarantee. It says it doesn't guarantee the thread. But this is a read. It's not going to free any resources. I'll just queue it that way anyway. So drivers can really have good information to make an educated decision to always get forward progress.
Excellent.
And that's what we wanted to address with that.
Right on. Well, speaking of forward progress, this is great to hear. This is great to learn. Thank you for your time.
Great.